So welcome everybody. Today we have a talk that's a little bit of a retrospective on what we've sort of learned over the past several years developing and maintaining some of the numerical tools, and responding to feedback from our users. So it's going to be a little bit more focused on sort of the pragmatics of making numerical tools more usable, ideally, with the goal being a sort of standard day-to-day toolkit that folks can, reliably and confidently deploy. And, because of that, we'd really love to have questions, talks, more fun when it's interactive. I actually don't have the Slack up, so rely on somebody to use the raise hand button in Zoom to let us know when there's a question. But please do keep questions coming throughout the talk as they occur to you. And hopefully we'll have some time at the end for a discussion about what's next for these tools. So to start things off, why do we care about having pragmatic tools for people trying to write numerical code? Well, compared to a lot of other sorts of programming, numerical errors are truly diabolical, right? Typically the error is silent. You still get an answer even when things have gone completely off the rails. The error is not compositional. Just because an operation has two mostly accurate inputs doesn't mean anything about the accuracy of the result. And a lot of times you get weird action at a distance. So you get error sort of traveling through the heap, interprocedurally, etc. And that's unfortunate because numerical code often needs to satisfy a lot of constraints. It needs to be accurate, but it also needs to be fast. It needs to be debuggable, etc. And over the past few years, we've seen a really rapidly evolving landscape with a lot of new numerical formats arising, many of them from the machine learning community, people trying to really push as many flops as they can while being accurate enough and often not having a crisp definition of what accurate enough even necessarily means for their particular application. But not to fear, if we go to Amazon and look up numerical analysis, we see there are over 10,000 results on how to write numerical code. So surely by now we can live in this ideal world where our intrepid programmer who's some kind of scientist or engineer has a formula they need to implement in their code. They go to Wikipedia, they find the formula, they type it in, and it just works. Well, we all know that's not the world we live in, unfortunately. And of course, sometimes the error is just because you made a mistake. So, floating point math, even when it's right, can still look wrong. And there's a funny XKCD to that effect. There's a link and the slides will be up after the talk. But of course, in practice, what really happens is, even when we do get the math translated correctly and our expectations are right, we get very strange errors. So I wanted to give a brief anecdote for the kind of situation that we're targeting, the sort of programmer that we want to build tools for. So our friend Blake Corder, who's a researcher in computer-aided design, was trying to build this set of interlocking rings. And these are produced by machining a graph of the complex zeros, of the zeros of some complex function. I forget exactly what the function was, but it needs to be accurate. And as you can see here in the lower left, a naive implementation, just assuming sort of real numbers, as if the computer could, evaluate with perfect accuracy, gives you very inaccurate results. Right? You're not going to be able to machine this design. So what we'd like, Blake's an expert, right? He has a PhD, he's a smart guy, but he's not a numerical analyst. So we'd like to give him some kind of almost like Clippy tool that he could just apply and get accurate results. So that was our initial goal when we first built Herbie back in 2015. And it actually did allow Blake to solve this particular problem. And from that, we've actually gone on to look at a number of different challenges that arise when people are practically trying to build floating point programs. So on top of Herbie, we've built this FP Bench library and benchmark suite we'll be talking more about. That was actually first announced 4 years ago at NSV. Other tools like HerbGrind for dynamic error analysis and Titanic for providing ground truth for sort of more exotic number formats. And what we want to do today is sort of talk about the lessons that we've learned as we get more users over the past 5 years, things that we were a little bit surprised about that matter to our users, and what we did to try to address that feedback we got. But first off, a quick bit of background on Herbie and FP Bench in particular, since that's what we're going to focus on here in this talk. So for those of you who haven't seen it before, Herbie is this tool where you write some expression over the reals. And Herbie takes that and tries to synthesize another version of the expression, which is more accurate than a naive translation would be when you consider floating point rounding error. And in practice, this tends to work pretty well for a lot of examples. And we have different error metrics. Here, we'll see a lot of these graphs today, but roughly on the y-axis, you see the number of bits that are correct for different inputs. And there's some averaging here. We can talk a little bit more about metrics later. But as you can see, we go from having answers which are often completely incorrect to, I don't know if you can tell, but here on the x-axis, there's actually a blue line. This implementation Herbie produced is essentially always accurate. And Herbie's also not perfect, right? So our goal isn't to have a tool that solves all numerical problems for everyone, everywhere, all the time. But the reality is that numerical expertise is quite scarce, right? The people in this call represent a pretty good chunk of the available numerical analysis horsepower that many programmers would have access to. And everyone's busy, right? We can't respond to every email and every Slack. So Herbie's what has been called sort of like a drunk numerical analyst. It is very thorough, but its key feature is that it's always available to everyone, right, whenever they need it. So I wanted to just briefly show you a quick demo of how Herbie works. You can try it out from the Herbie website. We'll actually just use the standard example. We'll be looking at some more interesting examples later in the talk. But if we take this example, like square root of x plus 1 minus square root x, Herbie figures out the right way to refactor that expression to get an accurate answer. And it provides a bunch of other information we're going to be talking about that sort of justifies that transformation and also lets you get a sense internally for what Herbie was doing to make that possible. And yeah, we'll sort of leave it at that. We'll see more here in just a little bit. The other project that we're sort of talking about today is this FP Bench effort. And FP Bench essentially provides three main sorts of things. It provides benchmarks, which we've mostly gathered from research papers in the community. The idea there is that previously there haven't been standard benchmark sets for numerical accuracy papers. And so we'd like to work toward a world where we have this shared resource, people can contribute benchmarks and run on them, so we can actually have a more apples to apples fair comparison across tools. It also has compilers in an effort to support analysis tools for different domains. So you can go from an FE Bench benchmark to C, JavaScript, Scala, Tech, Go, a bunch of other languages. And we've also put a lot of effort into standards. The idea is that there is no one canonical implementation of the FE Bench format. We'd like people to be able to implement it however works best for their domain, their users, but have some way that we can ensure the tools can interoperate. So those are sort of the big pieces for FP Bench. And if we go to the fpbench.org website, we've got exactly these sort of three main topics: benchmarks, compilers, and standards. If you go look at benchmarks, there's about 130 right now, a lot of them drawn from papers and textbooks. And for each of these, you can sort of, go look at that benchmark. They're expressed in the FP Bench format. And one thing that's really nice is you can also send them to various tools that support the features in that benchmark. So, if I click this, I can send this benchmark to Titanic and go play with it there. If I click this, I can send the benchmark to Herbie and go check out what it does there. On the compiler side, we have, sort of generic infrastructure for supporting working with this format. And the standards, are exactly what they sound like. They're sort of a high-level RFC-like description of what the FE Bench format looks like, so that ideally tools can be composed. Different tools that solve different problems can be composed to help address numerical challenges. So in the rest of the talk today, we want to go over sort of four main topics of things we've learned over the past 5 years, developing these tools, responding to user requests and concerns. We want to talk about how to help users trust the tools more, how we got insight into what the tools are doing in terms of measurement, and how we've been working to build community, and then finally, how we've tried to increase generality in the tools. So I think with that, I'll hand it off to Pavel to talk about trust.
All right, perfect. Thank you, Zach. So the backstory behind this talk, right, is that 5 years ago, we published a paper about Herbie, and we had the crazy idea that we should also try to make it available to users. And when I say users here, we didn't envision that being the research community, all of y'all who are at this talk. But instead, we thought about working scientists, people who had a need to evaluate mathematical expressions within their programs and did not really have the background in numerical analysis, nor could we expect them to get that background. So for these users, there's this interesting trade-off, which is that they would like to use these tools, but they don't know what those tools do. So why should our users trust Herbie, the tool? Zach introduced Herbie as a drunk numerical analyst, or quoted one of our users who said that. And that's a low bar for trust, but it is not a zero bar for trust. And in fact, previous projects have shown that, even if you are a fairly expert programmer, even if you understand these issues, there are still going to be bugs. And those bugs will be revealed by a careful understanding of numerical analysis. But if you've got a tool, as opposed to human expertise, that reveals a bug, then you've got to trust that tool more than you trust your own code. And so that's sort of the fundamental question that we needed to answer for our users, for them to be able to trust Herbie. So let's take this question seriously. Why should users trust this tool that two folks they don't know about have written? Well, to begin with, why do Zach and I trust Herbie? And, as developers of the tool, of course, sometimes we don't, but we do have some belief that the tool does the right thing. So why do we trust it? Well, we trust it because we know how it works. At a high level, Herbie's kind of got three stages. The first stage is to sample randomly a bunch of inputs to the expression that the user typed in. And for those inputs, we're going to compute a ground truth. We do that soundly using interval analysis. And then for the program the user typed in, we can estimate error by comparing the error of that program in floating point against those ground truth that we've computed using arbitrary precision interval arithmetic. Then once we've got this measure of how high the error is to start, we enter an improvement loop. In this loop, we store a set of different candidates that might be good. And Herbie's got a whole bunch of different methods for taking the original program, mutating it in some way that's likely to preserve its meaning and possibly improve accuracy. And then throughout this loop, we'll be evaluating each candidate to see how good it is, keeping the ones that are good on some points, and then mutating them further. And then at the end of this improvement loop, we've got a pass called regime inference. And that regime inference pass is all about, from this set of candidates, selecting the best expressions for each input point, inferring some kind of if statement that branches between different candidate programs when those candidate programs are good. So that's an explanation that we give in the paper and in the talks we've given about Herbie since, and also the explanation for why Zach and I think Herbie ought to work, because it's got the sampling, so it accurately evaluates error. It's got a loop. That loop does mutations we think ought to work. And it's got a regime inference pass that sometimes selects a good set of branches. But this is both a vague sort of trust. I mean, what if each of these individual steps had bugs? Or what if the random sampling were invalid or something along those lines? What if Herbie overfit? It's also a level of detail that we can't expect our users to grasp. We can't ask users to read our paper before they use our tool, because if they're the sort of folks to read numerical analysis papers, maybe they'd be numerical analysts instead of working scientists. So we need to give some kind of higher level summary of what Herbie does. And that summary can't be Herbie's output, because Herbie's output is sort of weird. You put in a single expression like this and Herbie produces strange output with formulas that don't seem related to the original. And also formulas sometimes that have gunk hanging off, like this 1 times and -1 times that Herbie produces. So ultimately, Herbie's answers are not immediately trustworthy. They're instead unpredictable and mysterious. So we need to give some kind of alternative summary of how well Herbie did. So the first place we do that is at the top of every Herbie output. It's this set of numbers that gives you a summary of what Herbie did. The way you read these is you say that Herbie took an expression that initially had an average error of 61.5 bits. And that means, by the way, that it's not just the mantissa that's wrong. It often has the wrong exponent. Maybe it's returning 0, or maybe it's returning nan instead of a normal floating point number. And it took that 61.5 average bits of error down to something like 2. Now, 2 bits on average, that probably means a lot of bits sometimes and not that many bits other times. So it doesn't mean that you're always within 2 ULPs of the answer or 4 ULPs of the answer. But it does mean that you've taken something that's almost always incorrect and converted it to something that is quite frequently fairly correct. So that's that first set of numbers. And importantly, when we're measuring the error here, we're using a sound method of error measurement, and we're using a test set, not the training set that Herbie used on the improvement loop itself. So that gives users some measure of trust. There's effectively a sound, trustworthy, and black box method to determine how accurate is Herbie's output. And then you see the other 2 answers that Herbie gives here, which are essential to evaluating, how good a job did Herbie do, and is it doing what you want it to do? So you can see how long it took Herbie to do this improvement loop. We use that, Zach and I, to significantly speed up Herbie, and we have over the years. And then the precision that Herbie is using, because if you're evaluating your program at the wrong precision, improving the error might not do what you want. So that's the first notion of...
it looks like we have a question.
Oh yeah, let's take a question.
Where does the test set come from?
It's also randomly sampled. So we have a training set of about 256 points that is used in the improvement loop. 256 seems like enough points for most expressions that users have. And then we have a that's the training set. And then we have a test set of about 8,000 points that we use at the end of the process to make sure that Herbie's doing the right thing. And you'll notice there that the training set is much smaller than the test set. One of the reasons for that is some of Herbie's internal algorithms, they're quadratic or they're cubic in the number of points. But evaluating error, that's definitely linear. And it's also important, again, for user trust, that this error measurement be as reliable as it can. And users evaluate that not just by knowing the number of points, they probably don't, but for example, seeing that it's reliable if they put in 2 different variants of a program, or seeing that if they try the same program twice, they get similar results. So using a lot of points, their users have ways of determining how reliable is that measurement.
Is the test set the same for every expression? There's just one fixed test set, or does it change?
It does change expression to expression, and there's a couple of reasons for that. First of all, different expressions have different numbers of variables. Okay. So you've got to have a different training set in that sense. Different expressions have different valid and invalid points. One thing we've noticed is that users do not really like being forced to come up with preconditions for their programs. So they will put in an expression, they won't use it for negative inputs, so you shouldn't either. And the way you know that is that for negative inputs, it produces nonsense answers. Maybe they're infinities, maybe those answers are nans. And of course, users can put in a precondition if they've got one, but we find that often they don't. So that's another way in which the training set has to differ point to point. And the test set has some similar notions of, it's sampling uniformly among the valid set of inputs. Finally, Herbie is random. So there's a seed that users can set, but if you don't set the seed, you're going to get a different training set.
Okay, thank you.
Yeah, these are important questions because the training set drives so much of Herbie, not just the notion of how well did Herbie do, but also internal notions. And we need to get that right in order for the results to be meaningful to us and to users. So this is one top level single number view of how well did Herbie do. But you might still ask, well, why should users trust that our interval arithmetic doesn't have bugs, that we use enough points, that this random sampling idea is even a good one? How do users trust that Herbie has done something sensible instead of produce a weird expression that only works due to overfitting of some kind? Well, for that, we have an alternative mechanism. And these are what we call Herbie's derivations. You see, when Herbie produces an answer, it doesn't just give you a single program and tell you it's good, use it. Instead, it gives you a series of steps that the user can also walk through to verify that the program is correct. So in this case, you can track that these steps are each labeled. They begin with first identifying a range where this program has a certain kind of error. And looking at it here, it looks like in this case, the error that Herbie is trying to solve is probably some kind of overflow. Overflow isn't a thing we tell users because many of them don't really know what that would mean. Then moving on from this range of inputs, we show a stepwise derivation. And for each of these steps, you can see first in blue, you see the part that's changed. Here in this derivation, it's the whole thing. But then left of that, you see an explanation of what Herbie thought it was doing. So here it looks like the key step is a Taylor expansion around negative infinity. And for each of these steps, you not only have the step, what Herbie did, but you also have a measurement of the accuracy after that step. So you can see a justification of why Herbie did each of these individual steps and see that they might be improving the accuracy. And this is useful to users not just to convince them that Herbie did the right thing, but also to help them correct for errors when Herbie did the wrong thing. Sometimes Herbie will make a step that reduces accuracy. And it might do that because it sampled a weird set of input points and didn't notice the accuracy reduction. Or it might have done that through some kind of flaw in its internal algorithms, and that's sometimes how we find bugs. But importantly, because users have this derivation and because they see intermediate steps in the process, they can see that if the accuracy actually increases from one step to another, they can go back to an earlier step. Or if Herbie did a bunch of steps that increase accuracy only minimally, users can ignore those steps and just take the trustworthy, simpler result that they find most compelling earlier in the derivation. So this is how we've looked into the question of improving user trust in Herbie. But improving user trust doesn't just happen at the top level. It also happens because we know that Herbie is doing sensible things internally, stage by stage. In some sense, this is internal trust. So let's talk a little bit about how we understood Herbie's internals, figure out how it works and why. And for that, I'll hand it back to Zach.
Thanks, Pavel. Yeah. So it turns out measuring a sort of synthesis tool like Herbie ends up getting pretty tricky. And where we really ended up needing it was actually often in debugging. So we saw this, complex pipeline of components that make up Herbie. And it turns out that each of those is fairly robust, actually, right? They're all designed to sort of find a version of a program that's more accurate. But what that means is that if there's a bug in a component, often other components will mask it, right? Because if one stage produced a bad program, well, the next stage is going to try to improve it. And when I say bad, I mean like incorrect, like it's algorithmically wrong. We couldn't find those bugs because end to end, you wouldn't see them. So we put actually a lot of thought and effort into trying to figure out how to make each component separately reliable and correct. And, like all large tools, we started off with big log files, which are essentially uninterpretable, right? It's an opaque blob of text, very hard to work backwards from, line 10,005 to what you need to change in the implementation. So over the past couple of years, we've been slowly adding, more and more insight into what's going on under the hood as Herbie's trying to synthesize a more accurate expression. And there's sort of key insights here that we actually think are probably useful for a lot of tools. One was really simple, almost just a generic software engineering insight, but to build a generic telemetry mechanism, to have a general way that every component of the tool can add information about what it's learning when to a shared database. And then we separate that from the visualization. And the visualization actually has been extremely important. As soon as we made the graphs or these timelines to show what's going on, big trends popped out, which allowed us to fix lots of bugs, but also have huge speed ups. So we'll talk a little bit about the most recent Herbie release, but we've had several orders of magnitude speed up in Herbie as a consequence of these metrics and being able to respond to them. Of course, there's also an added benefit to having these metrics, which is that they also improve trust. Now users can look inside and see what's going on. So we'll look at a report or two here in a second, but just from this little screenshot to highlight, there's a few features that are common to our metrics. One is the separation from a sort of global overview of what's going on. So at a glance, you can sort of see how a particular benchmark did in terms of the different subcomponents where resources were spent. And then also more detailed breakdowns for each component. Often, different components have different notions of what matters. They're doing different things. So you really want these sort of per component metrics to be hanging off of this global view. And then one really important enabling insight was to try to develop oracles where we could. So for some components, it's possible to figure out what a perfect implementation would actually generate. The one highlighted here is actually for regimes. So typically, regimes is trying to identify points in the domain of the expression where you should switch from one implementation to another to improve accuracy. And we can compare what the regime's inference system does to an idea where you could actually branch, have a different expression for every single input. So I'll just quickly show a couple of reports. We are getting a little bit closer on time, but here's this sine tan example. X minus the sine of x, x minus tan of x. Herbie does this rewrite. We have the derivation Pavel was just talking about. But now we're sort of looking more at the metrics. And here we see that almost all the time was spent in analyzing and in sampling at the end to, that testing set to establish accuracy. The internal algorithms like simplification, et cetera, took very little time. And you can sort of go through and zoom in on each of these phases. And I think we found bugs because of this visualization in every part of Herbie, and have a lot more confidence now in the accuracy of the tool. So this has been extremely enabling, and we've gotten feedback from users when they do stumble upon a bug or something. They help us more, right? Because they can go get a sense for where things might be going off the rails. So it hasn't just helped us improve user confidence, but also helped us in terms of getting better bug reports that are more actionable. So I think with that, I'll pop it right back to Pavel to talk about this sort of third aspect of our efforts over the past 5 years, which is trying to build a larger community around these projects.
Thanks, Zach. So, when we talk about a bigger community, what I mean, and maybe we should go back to like our thinking immediately after we published Herbie here, which is that, Herbie, maybe it's good, maybe it's bad. At the time, it was a little hard to tell. We just published the paper and who knows, what sort of bugs were hiding inside. But it can't be the only tool. So for example, if you're using Herbie, you're probably also interested in using some kind of bug finding tool so that you know what expressions to put into Herbie. You might be interested in some kind of error measurement tool that's sound because you're worried about worst case error. That's not something Herbie provided. So there have got to be a bunch of other tools surrounding Herbie that you also need to use. Herbie can only be one part of the puzzle. So the question is, how can we make it easier for users to use not just Herbie, but all these other tools that they're going to need and that Zach and I don't have the bandwidth to write into Herbie for them? And in fact, shouldn't write. The research community shouldn't produce a single research tool as a product. It should produce some kind of constellation of tools that users can use together. So for that, we figured we needed some kind of standards. We needed some kind of form of interchange. And that was the driving force behind our initial idea to build some kind of floating point benchmarks and standards and tools community. Now, looking back at that, the reason this has been successful and the reason that this effort has been valuable is because numerical research fundamentally is not an individual research group task. It's something that our whole community does, which is why we gather at places like NSV. This community needs all the things all communities need. They need opportunities for collaboration, they need communication, and they need some shared infrastructure so that research groups aren't independently rediscovering the same benchmarks or having to scrounge around for industry partners to get them realistic inputs or realistic floating point problems. One of the natures of floating point problems is you don't always notice if you have one. So having a collection of these floating point benchmarks, floating point tools, and floating point standards that make some of these gnarly problems visible and collect them in one place, that'd be super valuable. So the idea we came up with to try to satisfy these goals is something that we call FP Bench. And we've since used that as sort of a platform for all sorts of things. So for example, a month ago, we had an online workshop. We called it FP Talks, sticking to a brand name of putting FP in front of everything. So we had a bunch of talks from around the community, I'm sure of a bunch of folks that you know already. And by the way, all those talks are online. You can rewatch them, the slides are up, etc. So that's one form of community that we've been building. Another form is a set of tools that people can use. So, you've probably found that in your research work, you've had to redevelop a way to not just evaluate floating point expressions, but unroll loops, infer bounds, apply interval arithmetic, get error estimates. Well, having a common set of tools, and by the way, also tools like converting it to C code so you can measure performance, or converting it to text so you can put it in your papers. Those tools, it would be helpful if they could be developed once generically. And in particular, if you do it right, these shouldn't be particularly tied to the actual work you're doing. All we want is some generic AST and some way of turning that into C code, tech, applying inference tools, doing loop unrolling. So in FP Bench, we've developed a set of these tools. We've got an exporter to convert to languages. We've got transforms that do things like loop unrolling. And those can all be collected in one place and importantly developed once. But of course, there's also going to be a bunch of tools developed by individual members of the community that do something specific. And not only do something specific, but do something in a way that there are multiple approaches, where you'd want to have multiple tools to compare, where sort of the essence of research happens. And for that reason, we've also have this wonderful repository of community tools. I'd actually advise you check it out, and just for your own work, check if it makes sense to have it listed there. And if it does, send us an email. Right now, this community tools page lists, I think, almost 100 tools. I mean, certainly dozens of tools from papers over the last couple of years. We have some loose organization between dynamic and static, and we've got short descriptions of what each of those tools does. The other thing, of course, that we're trying to do is not just make this community more accessible to people outside the domain, people who haven't yet built these tools, people who don't know what tools are out there, people who want to see what is the state of the art, watch the FP Talks videos. But we'd also like to make it a little easier for people within the community to communicate with each other. One of the things we noticed with FP Talks is that oftentimes people were doing really cool work that our research could use that we didn't know about. Because of course, as wonderful as venues like NSV are, they don't happen once a week. So for that reason, we have this FP Talk Slack. It's free to join. It's totally open. You can find a link to it on the fpbench.org website. And that's been a great place to solicit benchmarks, but also a place to hear about announcements, see what other people are working on. People sometimes announce papers that they've recently published, or work that they're doing, or collaborations that they've started, which would be exciting for other members of the community. So that's another place where this emphasis on community means not just bringing the tools together, but also bringing the people together, and making sure that it's open not only to users, but also to ourselves. And as we've done this kind of community building, as we've tried to link more and more tools together and make it possible for people to use this idea of a constellation of tools together, we've also found that users have more and more that they want these tools to do. Users have all sorts of ideas for what floating point research could do for them. And that's really pushed us to identify a final goal for this community going forward. And that's to support this evolving landscape of user needs and user desires, and try to make our tools more general. So Zach will talk a little bit about that.
Yeah, thanks, Pavel. So, there's many dimensions that we can extend, all the numerical tools we build. Today, I want to talk about two in particular that we've been working on recently in response to feedback from users. The first is the need to support a lot of different representations. So a lot of traditional numerical analysis tools are focused, often just on doubles, but sometimes also single precision IEEE 754. But like we mentioned at the beginning, right? Today there's B-float, there's adaptive float, there's flex point, there's posits in a dozen flavors. And so how is somebody going to adapt their code that was written for doubles to posit 16? How about posit 16 to B-float 16? What about block floating point, right? There's this huge menagerie of formats. So one thing we've been working on is an extension to the FBbench core format that provides a sort of precision scope that allows you to precisely specify exactly how your computation is meant to be done in a way that all the tools that use that FBbench format can agree upon. And that's actually been nice. We're able to take examples from past research, like Cindy Rubio Gonzalez's work on precision tuning with her famous arc length example, and throw in new number types really easily. And what makes this work is this example, this graph is generated by a tool called Titanic that Bill Zorn, another student at UW, has been developing. And it's actually enabled other research we didn't necessarily expect. So once we have the ability to flexibly swap in different numerical formats, we can also do things like parameter sweeps to try to search for, for a given workload, what is the best number system? What are the trade-offs in terms of the, bit cost? How many bytes do I need to move through the memory hierarchy to do this computation? And what's the impact on accuracy, right? So it's this sort of complex landscape that we are increasingly trying to explore. The other dimension we've been really interested in is, supporting tensor code. So for a lot of machine learning workloads in particular, folks are willing to tolerate fairly high error, but all their computations are expressed over tensors, and traditionally FBbench has been more focused on simple floating point expressions. So to address that, we've recently extended in the just released FBbench 2.0 update. We've added tensor support, so now you can easily write things like matmul and other sort of core tensor operators. And we're working now to update additional tools and add support potentially in the near future to projects like Herbie. Although we are already getting a lot of mileage out of this, exploring this sort of landscape with Titanic. So be happy to talk more about it. I want to leave some time for questions, so I think I'm going to zip ahead. We can go over these, maybe in discussion at the end, but, in all of these dimensions, we think there's still a lot of work to do. There's a lot of challenges getting just ground truth results for arbitrary multi-precision, multi-format computations. What happens when I'm mixing fixed point and posits in general? How do I ensure my tools are analyzing or implementing that correctly? It's unclear how to do error metrics for tensor code in general. So that's a big challenge we've been thinking about. Community has sort of never done developing. Very excited to have events like NSV, events like Correctness at SC, things like FB Talks. But it'd be nice to, continue to develop a cohesive, unified spaces where we can build and share infrastructure together. And, and also with Generality, right? We're sort of always trying to support more users, better integration with existing tools. There is like this somewhat bit-rotted Haskell plugin for Herbie. How do we maintain that kind of stuff, have more people invested? And along some of those lines, there's a quick announcement I think Pavel was going to give.
Yep. So this is an appropriately timed talk because just yesterday we released Herbie 1.4. So we generally do once a year releases, and this is all of the work of late 2019 and 2020 put together. There's also a really exciting release because this is one of the first cases where we've seen a lot of Herbie's individual components graduate to the point of being useful standalone projects themselves. We've got an eGraph algorithm that's been rewritten in Rust, so Herbie's about 2 to 3 times faster end to end in just this release. We have a new take on interval arithmetic that you can find out more about. So check out the release, use it in any time you've got floating point expressions that you want to try to improve the accuracy of, and suggest it to all of your working scientist friends. So you can find that on herbie.uwplsc.org. And by the way, one thing I did want to say on the topic of this announcement and this talk in general, which has sort of been a retrospective for Herbie, is that it's really a bit unfair that it's just Zach and I giving this talk. Over the years, Herbie has been supported by a lot of our students, undergraduate and graduate, now at all sorts of institutions around the world, as well as some folks from industry who wanted to help us work on Herbie. So this short list doesn't really even include everyone who's contributed to Herbie. It doesn't even include everyone who has committed code to the Herbie repo. But these are some of the people who built the foundational components in Herbie. Alex wrote the eGraph engine. Oliver wrote the interval arithmetic library. Brett's been working on multi-precision with David. A lot of this has been done by our students, and I think it's important to acknowledge their contribution to Herbie. So I think with that announcement over, we'd like to leave a few minutes for a question or two, and then ideally, over the break, we can talk a little bit more about any of these topics that we've brought up. Thank you. I think these fundamental principles of trust and measurement make your tools more usable to users and community and generality. We found that a great way to grow our research and push in the direction of ever more research challenges and ever more novel insights to contribute to the world. Thank you.